You mix these together, made you a precipitate. We masked out the precipitate, correct? So I was kind of happy, and I'm not sure if it was just because we were shy, but it was also first hour. There's a normal question or mistake people make every time they do this lab. I don't know why, because I think it's really an obvious thing, common sense thing. But as I've often been told, common sense is weird because it's not very common, right? And we did have one group that actually paused and thought about this, which was good. It's really problematic though if people made the mistake. And so I don't know if people were shy making the mistake or not. But one of your questions is, and it's a very important question, is what was the precipitate, correct? One of those is obviously not the precipitate. Like clearly, obviously it can't be. Like there's one choice for the precipitate, it's obvious. And people have a really bad habit of picking the one that's obviously not and saying it's the precipitate, and it screws up the entire rest of the lab, right? And like I said, we had one group that thought about it and said, oh wait, that makes sense. But nobody else thought, which means either you did it right and are like me thinking, oh my gosh, it's so obvious, or you made the mistake, in which fact you weren't thinking at all because it was a Monday or a Tuesday, and that's sad because our brains need to be always operating, right? So looking at your products there, let's start with the obvious. Which one is obviously not the precipitate? All right, so which one is obviously not? And we're going to talk to this side of the room. So look up there. Which one is not the precipitate? Obviously. Now you're all scared, aren't you? You're like, if I say the wrong one, it would be just so dumb. It's true. I would laugh at you. Yes?
SRCO3.
The what?
SRCO.
Is obviously not the precipitate. Obviously, we were going to laugh at you. That's for sure. It's obviously which one is not the precipitate. There's only two choices, Poplitz. We just laughed at him for the other one.
Okay. NaCl.
Clearly, can you tell us what that's?
Salt.
Salt. Specifically table salt, but salt is great. That's good enough. Everybody knows what salt is, right? Yeah. Did you ever use salt? You do? What do you use salt for? You do? Do you ever put it like in water to help it boil? You do. And does it look all white and milky and pasty when you do it? Oh. No, it doesn't. When you put it in the water, what happens? Not a trick question. It dissolves, it disappears, right? Yes, anybody ever go to the ocean? We just got done on spring break. Big, huge thing full of salt water. Clearly, salt dissolves in water. It's not a precipitate. It's not the thing that made your stuff all milky, liquidy. Do you follow that? So again, that theoretically should have been obvious because you have, as Danielle said, she has experience with salt, right? She's made food with it. She's been to the ocean. She's seen it. She knows salt dissolves in water and is not a precipitate, which means, as Joey so eloquently showed us, it's a 50-50 shot. So if you know for sure this isn't the precipitate, then this one has to be the precipitate, right? I don't know if I spelled that right. Looks funny to me. Did you follow the logic there? And again, that's something that is, like if you had been asked it a different way, like which one dissolves in water, maybe you could have done it a little easier because you know salt dissolves in water, table salt specifically. But again, it was that problem where sometimes we don't think, and we really need to think. That is the quintessential chemistry thing. When people say chemistry is hard, and I sit up here and say it's really not hard, it's only hard if you make it hard. The reason why people think it's hard is because you have to think a lot. There's lots and lots of thinking, and you can't just take things for granted. And this is a time where people don't think. They just go, oh, it's a price. Oh, I don't know. I know that name, salt, 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 salt. Nope, doesn't work that way. So that's the precipitate. And what were we trying to find out in this lab? What was our main goal? Very quiet. David, what was the point of the lab? What were we trying to find?
They say SrCl2 got mixed with Na2CO3.
Mhm.
Trying to counteract it or take it out.
Kinda, not really. What did we care about here? It definitely had to do with the sodium carbonate or the strontium chloride. But what about those? What were we trying to find? Yeah.
How much sodium carbonate was in there?
Yeah, we wanted to know this, right? We had an unknown in our solution, right? In the liquid, we didn't know how much was there. And the lab was, which is not like a weird thing, right? Like if somebody gives you, here's one that happens often in my house if I let it. The girls will make Kool-Aid, right? Especially Cora. And she'll bring it out and there'll be like this much Kool-Aid on the bottom. Do you know what I'm talking about? Or chocolate milk. Yes. Shannon, you've done that a lot, right?
Yeah.
Oh, see, I knew it. And as a parent, she'll like bring her glass of Kool-Aid out with like this much. And I'll be like, how much did you even put in there? Right? Isn't that a normal parent thing? This is how we figure this out. Like this is the chemistry because Cora doesn't remember. Cora just pours whatever is in there. She's evil. So, not that you're evil, Shannon. I'm not trying to relate. You're an angel. Cora, not so much. So, we had to get something out to do that. These are both dissolved. They were clear solutions. We mix them together. We get a precipitate out. And that allows us to see, using Stoich, how much of the sodium carbonate we had. So how much precipitate did we have here? Oh, let's pick somebody. Lauren, let's pick you. How much precipitate did you guys get out in your lab? Okay, Morgan, how much did you guys get? Oh, she's looking quickly. Look at that. She knew it was going to switch to her.
Yeah.
You guys are really quiet today. Is it a tired day? Is Easter catching up with us? Thank goodness it's only a half day then, right? Yay, half days. 1.81 grams. Like this. Other people have somewhere similar?
Yeah.
Yeah, okay. If you're way, way off, the odds are that your paper was still wet or something like that, right? Remember, we had to leave it overnight to let it dry out. So like one group in first hour had like 6 grams or something. And I'm like, wow, how did you get 6 grams? And I'm like, it was still really wet. Well, that defeats the whole purpose because then you're measuring water, right? If yours had been really wet, which maybe your group's was, it depends on how you did things, what should you have done? Thinking again, I know. What should you have done if your paper was all wet? Yesterday when you came in.
Let it dry.
Let it dry. It's not like crazy hard stuff, right? And you have lots of drying ovens. There's 3 in the room. So if you're like, oh, we don't have time to let this dry, then put it in the drying oven, crank it on. It'll take like 5 minutes and it'll be dry. Throw it in a microwave. Let it dry out. Right? Because if it's wet, it defeats the entire purpose of the lab. Right? Like if the entire purpose, as we were trying to figure out earlier, was to find out how much sodium carbonate, and you get the wrong mass here, you're for sure going to get the wrong mass here. It's all just blah, right? It has no meaning. So now this looks just like a normal stoichiometry problem, right? You have an unknown, you have a known, and now we go through that process, which is what you probably should have done. And again, you can see where this would mess up if you chose sodium chloride, because you'd have had the wrong molar mass here, right? What's our molar mass for strontium carbonate? Is it 100 and something? 100, help me out. 40,
147.
147. Point what?
162.
So if you had done sodium chloride, you'd have had a different molar mass here, and that'd screw you up. Can someone do the math, or a couple people, so we have a check on it? Can you say it again? Did you say 226?
Yeah.
Okay, so we'll round it up. And that is moles of strontium carbonate. Yay for easy mole ratios. Strontium carbonate on the bottom. What I care about on the top. They were both ones. So life is kind of easy. Hey, that's our room number. That's convenient. We get that many moles. And then we can finish it off like we finish off every stoic problem. And what's the molar mass of that? 100 and something? 106? Is that what it is? Yay, 106 grams per mole. And can someone do that calculator math for me?
$1.299 to 1.3.
Okay. Is that what you got too, Danielle? And again, as you're looking at this, you can see this looks just like normal stoichiometry, right? I hope. Speaking of normal stoichiometry, how'd the quiz go? Easy. Nice. I haven't looked at them yet. Miss maybe you don't look like the easy one. It was a super hard. No. No, but it'll be easy for me to grade. I'll just be able to like zip right through it. Nice. Always nice to start off with an A. Don't you guys agree? Makes you feel good about yourself. But it's always a good feeling. Something made this possible. Part of your procedure made this work. So think back to your procedure, what you had to do, or look at it on your form, what you had to do here, like how it actually worked. Made this equation possible that we could use this. So think back to your procedure. What did you do in your procedure that made it so we could focus on sodium carbonate? Because that's what we cared about, how much sodium carbonate there was. So what did we do in our procedure that allowed us to do that? Second and think. All right, what allowed us to focus on just the sodium carbonate? What did we do in our procedure? Yeah, Ms. B.
Filtered it?
We're way before that. You're right. We filtered. The filtering allowed us to focus on the strontium carbonate because sodium chloride goes through a filter, right? Solutions do. That's one of their properties. They're little. Precipitates get stuck in filters. So that helped us get that and isolate it. But way before that, we made sure we were dealing with the sodium carbonate. And you might not even know it. It was very quick in the lab, maybe. Or maybe just you didn't realize that's what it was doing. So what did you do in the lab? Are you raising your hand? You kind of look like it. You're like, man, I got this. No. What do you guys think? What did you do that allowed you to be able to focus on that? If you're focusing on that, what are you not focusing on? How about that question? Speak loudly. You don't have to be so shy today. Someone was saying it, just quietly mumbling. We don't care about strontium chloride. So what did you do in your lab to prove that you didn't care about strontium chloride? What did you do in it? and made it so that the sodium carbonate was all that mattered. You did something. What was it? And by the way, it was probably the most important part of the lab. It's weird. People always miss it because it's not like right out there in bold letters. But it's actually crazy important. Yeah, tournament.
I don't really know, but was it when we added the, we kept adding until precipitates?
You did. You kept adding it. What did that do? Did you hear? She goes, we kept adding strontium chloride. Do you remember that part? It said, hey, add, what did it say? Add 20 milliliters. And then it said, add some more until it stops. And so you were like, oh, okay, I'll add 20. Did it stop? I don't know. I don't know what that means. Let's add some more. All right, stir it up. Well, I can't tell. It's all white. I don't know. Well, let's add some more. For me? No, well, let's just pour all the rest in. I guess it stopped now, right? Did people have that happen in their labs? Exactly. Oh, good. Right? So that's, you clearly didn't care about this because you just kept pouring it in. Why? What were you making sure happened? Mr. Kernick, since you started us down this rabbit hole, what were you making sure happened? You kept adding that and adding it and adding that. What were you making sure of?
Maybe that, like all the possible precipitate that could be formed between that reaction happened.
Why would that be all the possible? Why wouldn't it keep forming?
Honestly, don't know right now.
Think more. Think more. Did you guys get her logic right now? Because we wanted to get as much of this precipitate as we could get, so we kept adding this. Why would that give her the maximum amount? Yeah.
Because like you use up all the sodium carbonate.
This gets used up, which is really important because that's what we care about. We want to make sure all of this is gone and that all of this turns into this, right? Why did the reaction stop? This is that important part. Why did your reaction stop? She kept adding strontium chloride. Why didn't it just keep going? Not a trick question, honestly.
This is not sodium carbonate, then more like the ratios off, I guess.
Not just off.
This-
Yeah, it's gone. You were right with what you said first. Did you hear? She goes, because this ran out. This was gone, correct? You kept adding this over and over and over. There's still plenty of this in there, right? It would have run out. This would be all used up. It'd all be gone. Do you follow that? We say that this stuff was an excess. That's not the term I necessarily care about, but we say we had lots of it. It was tons and tons of it there. What we actually cared about with this guy, that sodium carbonate, and it stopped the reaction, right? This is our limiting reactant. And like all things you've been finding out in chemistry, we're not really a creative bunch. Like we call it the limiting reactant because it's the reactant that limits it. It stops the reaction. Why does it stop it? Not through any magic. It ran out. Why did it run out? Because you kept pouring the other stuff in. Like, this isn't like weird, crazy magic. Let's go back to one of your other labs you've done. Let's do, the paper lab. Remember the paper lab? Ripped up paper, you're trying to see what burned it. All right, so in that lab, when you were doing it, what was your limiting reactant there? What's happening when you were doing your burning paper lab? It could have been your paper. If it was your paper, that means your paper did what? Yeah, it burned all up, right? And you just were left with a pile of ash. But what happened if your paper didn't burn up, Miss Beebe?
There was enough oxygen getting to it.
Then there wasn't enough oxygen, right? So your limiting reactant isn't always whatever it is. You made this be the limiting reactant, right? And the same thing with your paper lab. In some parts of the lab, the paper was limiting reactant. The paper burned all up, right? In others, it was the oxygen. You made it so there couldn't get enough oxygen. It wouldn't even burn. Oxygen was clearly the limiting reactant. Do you follow this? So that is kind of the main concept for the rest of this unit, is this idea of limiting reactants and how we control it or when we want to. So sometimes we don't care. This slide was a good one. We don't care. We're going to put in as much of this as we can because this is what we care about, right? So we just keep throwing it in. Sometimes we actually care that we want everything to be perfect as much as we can make it so that everybody's a limiting reactant or nobody is. But it starts with figuring out what that looks like. Now, here's the easy part. Really, really hard. It doesn't have to be. All you're going to be doing is the stoichiometry twice. And if you remember, it's just stoichiometry twice. Limiting reactants tend to be rather trivial for people. What gets people in trouble is when they try to think too much and figure things out, and then they're like, I just don't get this limiting reactant stuff. And I'll be like, do you get stoic? Yeah, I aced the quiz. Then you clearly get this. You're just being silly, right? So if you could do the quiz yesterday, this will be easy. And let's use this one as an example. A typical limiting reactant problem, non-lab based. Can I erase this? You guys don't mind, do you? Would say, all right, figure out your limiting reactant here. And it'll say, if you've got, let's pick something, 3 grams of each. So if you have 3 grams of each of these, which one of these? So a little bit different than what you did. In your lab, I gave you strontium chloride that I already massed out, had already done right. And you just kept adding. But now what if we did this? Now, first things first, if you get something in grams, what should you do? Switch to moles every time, my friends, every time. So go ahead and do that. Change those grams to moles. Let's start there. What's this? We're having a campground? Are they talking pop cans or like food cans? Food cans. Who's doing the drive? So I have lots of pop cans.
You always put pop cans in. Buy food cans.
My food cans and then put the food cans there. Probably full food cans though, right?
That
Here. All right, so I'm going to choose sodium carbonate here. And you guys told me a little bit ago that that was 106, right? Is that what you guys told me?
Yeah.
And what did you get for that? Yeah.
0.0281.
Hopefully, why it's important to always write these compounds down, because we're going to be writing so much of this. If we don't have the compounds down, we might get confused with each other. Strontium chloride. Ooh, I don't know. What is that? Like 150 something? Huh? 157. Got confirmation?
Yeah.
Yeah. It is 0.019. Yeah. Sweet. Now I'm going to do this a little differently. There are lots of ways to do a limiting reactor problems, lots and lots. I do mine in a way where I don't have to think at all. Right? I like being lazy sometimes. You can do it however you want to do it. I don't want to think. So what I'm going to do is take this one step further and say, okay, what do we care about in this lab? What's the next question going to be? You know how there's all like A, B's, and C's? So since we have this as a precipitate when we were doing it, I'm going to change this using my mole ratio to that. I feel like it. There's no logic. I'm going to do it for both of them so that I'm comparing something that is the same. You know, just make it so I don't have to think if I'm looking at something that's the same thing. So I'm changing these from moles of sodium carbonate and moles of strontium chloride just to give me moles of strontium carbonate. Follow the logic? It's easy math for me because of that ratio. Oops. Notice how this is just sodium again, right? Thing brand new. And now this makes figuring out the limiting reactant really easy because if this made, let's just pretend, 28 of this, and this made 19, well, that means which one was the one that ran out first? Probably the one that made the least amount, right? Would have run out. So if this only made this much, this reactant. So this guy, that strontium chloride, must have been what limited this reaction. Do you follow that? If I can change all to the moles the same thing, then I can just look at who's smaller, and that reactant that did that was the limiting reactant. Do you follow that logic? Now there is a faster, easier way, right? I could have stopped here and used my mole ratios, right? Because the mole ratios of sodium carbonate to strontium chloride is 1 to 1. I'll say who's going to run out first. Do you follow that? Sometimes it's rather tricky. Like if the ratios are like 2/3, right? Or 4/5. That tends to make it a little bit harder to just visually look at it. Sometimes these numbers are kind of weird and funky, and so it makes it hard. I just always take it to a product. I always just choose a product that's either next in line in the question or is next in line for the lab to do it. It doesn't take me long, I figure, to do the one extra step, and then I don't have to think as much. And it saves me time if the next question was, well, how many grams of strontium carbonate would you get? Well, then I'm already there. I've already gotten it to here. Do you follow the logic? Okay, let's try another problem. Let's do this one. What substance is this? Start. What is that? It's combusted. Do you know? What is that C? I was all excited about maybe using that, but I didn't have time. That is called propane. Which at this time of year, where do you all see it? Yes, sure. In your grills, right? All your grills, if they're not charcoal, tend to burn propane. So this is what happens in your grill. And yes, they sell them at gas stations, big, huge white tanks, normally locked up in a big blue cage. They won't blow up everybody in the gas station, just people outside of the pump. It's always nice. So let's see. Let's say I had 100 grams of that. And what if we had, I don't know, 200 grams of that? So let's give ourselves lots of oxygen, a little bit of propane. Why don't you figure out the limiting reaction for this? Stopping this reaction. Who's limiting it? There will be a second part of this question in a minute. Right, so let's kind of start this. I'm going to start with the propane here. First thing we got to do is balance it out, right? I don't know, Fitz, what's the balanced equation here?
1, 5, 3, 4.
1, 5, 3, 4. Right. Seems pretty traditional. Now let's work this through. We got 100 grams of propane. And what is that? 44. Is that right? Per mole. My grams are going to cancel, which is what we want. And that goes in there 2.27. And it's the same thing for oxygen. We got 200 grams of O2, 32 grams per mole. Sometimes you'll forget that's O2 and then just put it on 16 here. And it screws up a lot of the rest of the problem, so make sure you get it correctly. And that goes into that, I don't know how many times, 6 point something? 6.25? So I could look now and see if I can figure it out. I think I can, right? Because what's my ratio of propane to oxygen? Not a trick question, ratio. 1 to 5, right? So I can look and say, is this being the 1 to 5 ratio? If I had 2 moles of this, I would need how many moles of the other? 1 to 5 ratio. This would have to be 10, right? And is it? This is probably going to be my limiting reactant, right? I'm going to keep going. Like I said, this is a 2-part problem, and I want to be sure. I don't want to have to think it through like I just did. So I'm going to change this to carbon dioxide. The greenhouse gas tends to be pretty popular to talk about. And I'm just using my mole ratios. So that's a 3. Propane was a 1. This is a 3 and a 5. So far? All right, so this looks like 6 moles of CO2. And this one, oh, that one I can't do in my head. What's that one work out to be? 3 point something, 4 point something? 3.75, do we have agreement? Yeah. And using the trick I taught you before, you just look at whichever one is smaller at this point. It's this one, which means this was my limiting reactant. This guy, and we tend to label it as LR. And the second part of the question is, how much CO2 did this make in grams? Well, if I've already done this, then it's an easy problem, right? This times 44 grams per mole, and I'm done. If I had stopped here, I'd still have to do more steps, right? So that's why I always just go through, so it's quick and easy at the end. You can see by it is not necessarily whatever you have the least amount of, right? This only had like 100 grams. This had 200. The 200 was limiting reactant because it's a 5-to-1 ratio, right? And oxygen's really small. So this 200, did become it. So the grams don't matter, as we talked about before. It comes back to our moles.
So you were trying to find how many CO2.
Yeah.
So you multiplied it by 44 grams per mole. I just divided it
Right here.
to the bottom line.
I did this because this is my molar mass of CO2.
No, why did you multiply the bottom of the top? Yeah.
Because it's my limiting reactant.
So you want to get the limiting reactant.
Yeah. In fact, what people will do is once they figure out what the limiting reaction is, so just like we did, and we said, oh, it's oxygen, both times. Do you follow that? So whenever I realize that this is the limiting reactant, what people will often do is this. Because that doesn't matter anymore. Just like over here. It didn't matter how much of this I put in, remember? You kept pouring it in. You could have poured in my entire thing back there. It wouldn't have changed the reaction because this limited it, right? So once I know that somebody is my limiting reactant, that's all I care about. I don't care about anybody else anymore. And you need just to cross it out. Common mistake for people who don't get it on a test, I'll say, hey, how much like CO2 do you make? And people add up like every single line they did. I'm like, what are you doing? Well, don't I do that? No, in fact, you should get rid of everything that wasn't limiting. Because the only thing that matters is limiting. That's why it's so important to find. Yes.
Okay, so like after you find your limiting reaction, which is
Reactant. Yeah.
which is oxygen.
Yes.
So then when you said this question with how many grams you have,
Yeah.
you would then only do that one.
You got it. Yes, ma'am. That's the only one you deal with. And if I then had a third question and said, hey, how many grams of water would you make? Again, guess who's the one I'm gonna look at? I'd only look at this. In fact, I would skip all the way down to here, and I would do my problem from here. This ugly, so you can see. So if I all of a sudden changed it to water, right, I would just jump and start doing it like this. So you can see the general principle of stoichiometry is still the same principle, right? And decide who's the limiting, and then forgetting about everybody else as you do it. Other questions on this? So this is what you were dealing with yesterday, and that is taking an unknown, right, forcing it to be your limiting reaction by adding excess of whatever else it is, then measuring your precipitate and using your stoichiometry to figure out how much you started with. Normally, it's doing it just like you with a filter and a funnel to do it. I think that's why they call it gravimetric, because gravity, right? Your gravity filter. I'm not sure. Like, I've never looked up the history of the name. In my brain, it makes sense because you're using gravity filtration. It's called gravimetric. So, but the gist is that, yeah, you're taking something you don't know, adding in excess to give you a precipitate, and then measure that precipitate, that thing you can actually measure, right? Because you can't measure the other part. And we do this again, that's the first lab in AG chemistry. You're given an unknown, and they're metric analysis and figure this out. Your next lab is a gravimetric analysis, where it's like, hey, figure this out. And we use gravimetric analysis to do it. And the gist is using stoichiometry, add excess, so you have a limiting reactant, so that's all you care about, and then work through from there. Yes, ma'am.
This may kind of be a dumb question because I don't know if you said it,